good afternoon. So let's start. Today after class, first graded homework will be returned. TA is going to upload, release the grading because he graded through Canvas. So we have, I have, 1 week regrading policy. So the solution will be also uploaded too. So first I want you to check, and then like randomly 2 questions are, selected. So if you want to, ask some questions, first, I want you to go to TA because the partial point I trusted him. But of course, I'm available to talk, of course, But first, I recommend you to talk to him because the partial point or something I think he, counted. And then also, second announcement is about the exam. Next Monday, I think we have first exam. And then, we will study today. And then Wednesday, I want to still cover some material. Then maybe end of the Wednesday lecture, I will start talking about the exam, what sections we will cover. I know I started the email, receiving emails about, exam. I'm still making, so I cannot answer to you, how many questions, what's included. I'm still making, in progress. But Wednesday, maybe, you can start asking. I mean, I cannot tell which question the problem will be in the exam, but I will also, tell clearly which sections, because we skip some sections, right? And I left some keyword. So I will clearly tell which section, but I cannot tell line by line. So I will tell which section. So then I want you to, of course, read the textbook. And then also some students need some special accommodation. So DRC, I believe some students need some help. And then this class, we are having this NEB, right? Right after class, we have another class immediately. So I want, if you need some accommodation, special, help, I want you to take exam at DRC. So please fill the form. I think there is a kind of, 4 days rule or 3 days or something rules. So please go to the website and then read all the requirements you have to do. And then you have to, I think, request some accommodation. I have to approve it. So that requires some date too. And then I've already input all the exam dates, not only exam 1, exam 2, and the final. So if you need help, please go to the website. And if you need any help about, like this DRC, I think you will have, I think you have information in the syllabus. But also, please, contact me or TA. I think I cannot help, but I can guide where to reach. Any questions? It's good. Okay, so let's continue casting process. So I think we can start. Today is like 16th. So continuation of sand casting. Okay, sand casting. So let's take a look at the textbook. I just want to share one of the figures because we watch video. Then video just kind of goes through, but I think you can watch, right, through the course, videos. So anyway, this, the projector. Yes. So then this is, page 147. This is the figure 3.25. So I mentioned, the gate system, because now in this case, you will make some cast. This is a cast part, right? This, this part, casting, it says that, So, but we don't pour this molten metal directly. We will use this, kind of passage, which is called gate system. Because if you pour directly, when you make, zero, sometimes spits out a turbulence or every, like kind of contaminants may be, included, right? Or involved inside, which we don't want to. So that's why we have this pouring basin, like sprue, and then gate, and then change. So this is like a runner. This system is gating system. So this is a well, so some sort of reservoir. And then you change the direction. You don't want to have 90 degrees, so that's why there is some sort of, kind of curvature and the reservoir system, and then go to, the sections you want to make. So then this, I think the important part is riser. Sorry. So in the video, I think you pour, not you, somebody poured kind of maybe aluminum, some silver, molten metal, and then, you know, it's open, right? Open laser. Because trying to keep the pressure, you know, as atmospheric pressure, and then also, you know, like degassing. That's important. I think, you know, this, you know, also included in the video, but I wanted to kind of emphasize, you know, that what is gating system, why we need that kind of passage, you know. And then, you know, there are more detail we need to, you know, kind of know. That's going to be included in the supporting material, which I mentioned in like maybe Wednesday or Friday. I will prepare some questions regarding this casting or today what we are going to study, because we don't have time to review as a homework. So we will do some questions together, and then I think you can understand more why it's so important, what kind of things we need to pay attention. Good? Okay, so let's move on. This is still under the, you know, expandable mold, you know, process. So there is other process, which is shell mold casting. So we will watch video after this, you know, and then, you know, another is polystyrene, you know, expandable. Pattern. So last one, roast wax. Huh, interesting, roast wax method. Method, but investment casting. Okay, so these are, you know, like, you know, three kind of, you know, others. There are others too. Major processes people use, but I want to, you know, use video. So first, you know, actually, you know, I want to go with the polystyrene and the roast wax, because last time I kind of stopped the video, right? So rest of the video covers these two processes, and then shell mold is a different video. So I think we can watch, you know, three of them, and then we can just kind of summarize. By the way, where is my mouse? I'm trying to look. Can you see my mouse? Maybe this way. Then I think, sorry. Okay, yeah. So this investment casting and so evaporative foam casting, that is, you know, polystyrene, you know, casting. So okay, so let's watch from here.
Investment casting is a precision process using primarily ceramic shell molds. Investment casting is also known as the lost wax process, because wax, a principal pattern material, is consumed during the mold-making process. Consumable plastic patterns are also used. Investment casting patterns are made by injection molding. These patterns are assembled onto a wax post connected to a pouring cup. This pattern assembly, called a tree, usually incorporates complex runner systems to assist metal flow in the investment casting process. The shell mold is produced by dipping the pattern assembly several times in slurry and allowing it to dry between dips. The first slurry mixture consists of fine particles for smoothness. Subsequent dips are mixed with coarse particles to quickly build up thickness and provide strength. The wax is removed from the mold by melt-out in a furnace or autoclave. Then the mold is fired to remove moisture, cure the ceramic, and to preheat it for pouring. Both ferrous and non-ferrous metals can be investment cast. Once the metal has solidified, the mold is broken and the casting removed. The main advantage of investment casting is the complexity of shapes that can be cast to close tolerances, thin walls, and smooth finishes. Most investment cast parts weigh less than 4.5 kilograms. However, parts weighing over 100 kilograms are also made. Evaporative foam casting refers to the use of expendable polystyrene foam patterns in molds made of dry, unbonded sand. The process is also known as the lost foam or expanded polystyrene process. The pattern may be a single piece, or for complex shapes, an assembly of molded pieces. Patterns also can be clustered in groups to produce multiple parts at a time. The pattern is coated with a thin, high heat-resistant coating, usually silica. Once the coating is dry, the pattern is placed in a flask and surrounded by sand, which is vibrated for compaction against the pattern. Casting then proceeds with the poured metal evaporating the polystyrene foam and filling the cavity formed by the pattern.
Okay. So the first one, investment casting. So lost wax, so you use wax, but to make this wax, you will have injection molding. So then you will have dye, right? Complex geometry, and then you can make, this, like dye, like a hollow shape, and then you pour wax, and because of that, like video said, you can make complex geometry, but usually we don't make large one. Large one, probably sand casting, right? Like machine tool, like base, you see the big, like a steel block, right? So that's like sand casting. Because again, except for the, kind of sliding phase, the surface, who cares, right? Right? Machine tool, did you take a look? Right? Sand surface is fine. But this kind of complex geometry, probably the surface is important. That's why you use, injection molding to make smoother one. And then melting, and then, you have a kind of hollow shape, and then you can pour, you can make it, right? Like polystyrene-wise, you don't melt. When you pour the molten metal, instantaneously you evaporate polystyrene. So it's not like two-step. It's one step, you pour, and then instantaneously you evaporate, and then you will kind of fill the, this kind of cavity, and then you make, parts. So these are the, two different, style. Then others, shell mold. So that's, let's see. This is animation. Half of that. What's the blue? Okay. So basically, this one is, similar to like kind of sand casting, but not like such kind of greater, thing, like kind of smaller parts. Then all of the process, you see silica, fine particle can be maybe the first surface because you want to have a better, like it depends on your application, of course, better surface. But if you use only the small particle, permeability is going to decrease, right? Permeability, gas leakage. You want to, remove the gas, right? So that's why maybe second, third layer, you can use large one because this is not going to influence any of the part surface quality, right? So more like a supporting casting, solidification process. Then you can create this pattern. Now you saw the core, right? So core, you have to remove, right? After that, right? So collapse, So like a kind of clay, like a silica sand, like put together. After that, you can, hit. This is the example, but it has to be removable. You cannot use solid stuff. So that's also a trick to make complex geometry, right? How to fill it and then how to remove. Like engine block, cylinder block, if you are interested in automotive, right? Like block, right? Cylinder, piston go back and forth, right? So that's also casting process. That's mostly sand casting. And then after that, they have to remove sand. Basically, people are hitting. Just hitting. Can you imagine your job is whole 8 hours, just hitting a cast? Maybe you can, develop some, machine to do that, because you have to remove all the sand from the engine block. Otherwise, once you start, engine, if something contamination happened to the piston, it's not just oops, right? It's very dangerous. So anyway, casting is very traditional, like old-fashioned, but they have a lot of, advantage. Even smaller parts to large parts you can make, right? And then depends on the, of course, size, and then complex geometry, not like like investment casting, but you can manage, and then less expensive. So that's also important part. Yes?
Does using sand as a medium create a temperature limitation for the process?
So depends on the sand. That's why silica, like high temperature resistant. Otherwise, maybe sand is going to be damaged, or even like not only sand is okay, but mold has to be stiff enough, right? Because if you pour quickly, or even like flow rate is high, or pressure is too high, it's called a mold wash. So then this sand is okay, but this shape is going to be, kind of wiped out, So yeah, we have to care about that. Yes?
Are the halves used in shell mold casting expendable, or are they reusable?
Expendable, okay. Yeah. Yeah, after you remove, you break it, yeah. Okay, so this is kind of example. So how about the permanent mold? So that's going to be the next topic. Permanent mold. Come on. Computer is sleeping. They don't recognize me with my glass. Really?
You look like a whole new person.
Okay. Okay, good, Okay, so now next to, 3.7.2, permanent, So this advantage, So first, good surface. Part surface, of course, Compared to, sand casting, because you will make mold. Permanent means not like permanent. Nothing is permanent, Of course, it's going to worn, right? But you can reuse. So this. So sorry, I don't know. You can reuse. That means permanent in this, casting world. So then, drawback. Of course, there is some limitation. Complexity. But nowadays, actually, it's very complex, parts can be made using this permanent, mold casting, permanent, casting. Of casting. So example-wise, actually, you know this process very well. Maybe I can use this one. This is a kind of application. I believe at least you had one, something. I just opened it, right? Die casting, right? So that's this process. And I said limitation, complexity, right? But look at this. Door mirror, and this, like any body or even, fender, everything, right? So precise. How much do you spend to buy this? Or how much did you spend when you were younger? $100? $1 or $2, right? Like Hot Wheel or something, right? So which means it has to be mass productionable, right? Otherwise, you cannot pay, whatever you pay back, if you are a manufacturer, right? So anyway, these are the very like major application. If you still have this at home, please take a look. Or you go to some store, you will be super impressed how precise this is, And whatever, even this, look at this. Because die, right? You cannot use probably aluminum, right? You have to use heat resistant material because you will reuse. And then molten metal, even if some metal, like steel, high melting point, right? And then maybe aluminum, compared to steel, maybe lower melting point, but what temperature you are talking about? You have to machine, right? So when we talked about machining and then some sort of titanium, why it's difficult to machine? Why superalloy is difficult to machine? Work hardening, thermal conductivity, right? So thermal conductivity, these materials, very difficult to machine because it's not so easy to be softened, right? But to make this and to provide, especially for toy for kids, for toy for adult, some premier toy, I'm sure if you are a collector, you will spend a couple of $100. But if you are like, toddler, they don't even have money, right? The parents have money, right? So how much, they can spend. So, when really, once you go to some store or if you have it, appreciate. Not for car, appreciate for engineer, you guys, Yeah. Then you will see, this is die casting, So let's get back to note. We want to share some, a little bit more information. So two kinds of die casting. One is hot chamber die casting. So this work for lower melting point metal. So some example is like a zinc or something. And then, figures, 3.33, 3.34. I should put S. Okay. And then the pressure, low pressure, Another, or the other, is cold chamber die casting. So this is relatively speaking, higher melting point metals. So like aluminum or copper or something like that. And copper, I put alloy, So this is more like a higher temperature, 15 to even 150 megapascal. Okay. Then this is figure 3.35. Okay. Pressure. I don't know if you have a sense. Megapascal pressure. Where do you feel your pressure? Tire pressure, maybe? You have a sense? So when you drive a car, check tire pressure. I mean, for safety, of course, but just to feel. Because again, I'm trying to train you, right? At the beginning, I said that. It's very important for you to train yourself, the sense of, whatever value, miles, kilometer, or even this case is pressure or even weight, right? If you work with somebody, right? If you're holding somebody and something, right? You need a wrench. You need something, tool, right? M3, M5. If you have to say, no, I'm holding very heavy one, but your partner doesn't have no sense, the wrench side, you have to hold it. You will be upset. It's also dangerous, right? So this is the example. So pressure, okay, megapascal is very difficult. But, just try to, get some idea. But let's watch video, because these two, why it's hot chamber, why it's called cold chamber, and also why hot chamber can be used for low melting point, I mean material-wise. So there is a kind of information included. So let's go to the video. Die casting.
There are several types of die casting machines in use today. Most of these machines are hydraulically actuated and operate horizontally, but vertically operating machines are also utilized. The principal difference between vertical and horizontal die casting machines is, as the terms imply, the direction of metal injection into the die. All die casting machines include a metal injection system to get the metal in the die, and a clamping system to keep the die halves closed during injection. The two principal types of die casting machines are the hot chamber and cold chamber type. The hot chamber machine is used mainly for die casting zinc and other metals of low melting temperature. However, it is also used to die cast magnesium. The machine's shaft or charge end has a holding pot, which is a reservoir for the molten metal seated in a furnace, and an injection system for transferring the metal through a gooseneck-shaped pipe to the die. The plunger end of the injection system and the lower portion of the transfer pipe are submerged in the molten metal. For this reason, aluminum and copper alloys are unsuitable for use, since they chemically attack or erode the submerged injection system. When the plunger rises, a charge of metal enters the pipe through a port. When the plunger descends, it closes the port and drives the charge through a nozzle at the end of the pipe and into the die. Injection pressures may range from 1,500 to more than 4,500 pounds per square inch, or 10 to 31 megapascals. The cold chamber machine is used primarily to die cast the aluminum, magnesium, and copper alloys. In the cold chamber machine, the charge is supplied by ladle or feed system from an external furnace source to a holding pot at the shot end of the machine. The feed system components are not submerged in the molten metal. The charge is poured ahead of the plunger tip through a pore hole in the shot sleeve. As the plunger advances, it closes the pore hole and drives the molten metal into the die. Injection pressures may range to 10,000 pounds per square inch or 69 megapascals for aluminum and magnesium, although some machines can provide still greater pressures. After the metal in the die solidifies and the die halves are separating, the plunger thrusts forward, extending the plunger tip past the cover die. This pushes the biscuit that solidifies at the end of the shot sleeve, assisting casting release. Dies are usually produced from hot work tool steels, mold steel, Mar-aging steels, and to a lesser extent, refractory metals such as tungsten and molybdenum alloys. All tooling materials are noted for high hot strength and high temperature wear resistance. Dies are usually made by machining from blocks of wrought metal, but they also can be cast and machined. Because of their machined features, precision, and materials used, die casting tooling is expensive, but the dies are reusable for thousands or even hundreds of thousands of parts. The cover die half contains a port for entry of the molten metal from the metal injection system. The ejector die half usually contains the channels called runners through which the molten metal flows to reach the gate or gates at the die cavity. Dies are typically single cavity or multiple cavity dies. Multiple cavity dies are usually used for multiple identical parts. However, they also can be used to produce parts of different design, and if so, they are commonly called combination dies. Because such dies are often used to cast parts that will be assembled together, they are also called family dies, meaning dies for a family of parts. Cores, fixed or movable in either die half, are used to cast holes in various directions. Fixed cores are in line with the direction in which the die halves open. Those for holes in other directions are retractable on moving slides, also called core pulls, to move in and out with each shot. Inserts, placed in position before each shot, also can be used to cast complex features or to be cast in place as an integral casting feature. To minimize porosity in the casting, the die halves have vents to release the air that is pushed ahead of the metal shot. Overflow channels in the die blocks catch surplus metal. They also assist in venting and provide locations off the casting for its ejection. Built into the die blocks are cooling lines, circulating water or oil to dissipate the heat of the molten metal at a precise rate. Cooling at a controllable coolant flow rate is important because it controls the metal solidification rate. An ejector system is required to release the casting. In the system, ejector pins are mounted between ejector plates in a pocket on the ejector side of the die. In most cases, they are activated by pneumatic or hydraulic cylinders. To facilitate casting ejection, dies and cores incorporate a slight draft or taper, the amount depending on the metal to be cast. In general, the lower the metal's melting temperature, the less the draft required.
Okay, sorry, I shouldn't move the mouse, but I hope you get the idea. So let's go to this screen. So figure, I use like figure 3.34. So this is hot chamber. Okay. So the important part is this called gooseneck. I believe video said. So this piston is always submerged, right? So this is for low temperature melting point alloy. So then pushing in and then go up and then you feel the another kind of set of the molten metal and push. So that's how it works. Again, key is this gooseneck. But other, this cold chamber, this is figure 3.35. So this is high melting temperature alloy. So they use ladle. It's like a spoon, big spoon, right? And then pour. Because it's so high temperature melting alloy, you have to keep high temperature, right? So what kind of material can be used to kind of hold this molten metal. And then, how much you can do that. So then you pour, then high pressure, then you are going to push it. So basically, based on the principle, then you have to, kind of differentiate which one is better for certain applications. So these are two major, die casting. So die is expensive, as video said, right? So this is just general information. Die is the heart, core of the manufacturer. So, usually, I hope if you in the future, you don't have any experience like bankruptcy, so then company, like if they use die mold, if they are, taken by banker, they cannot make anything, right? So banker comes first to take die. That tells how important it is. Then, of course, company makes a lot, it's very expensive, right? What kind of tool can be used to machine such kind of, tool steel? Because tool steel is to made tool, right, for tool. But tool is going to cut the tool. That's not so easy, right? So then look, you see the smooth surface, right? Like again, today, even if you don't have it, just go to some store, look at some, car, like toy cars. How smooth they are. Really, even coating, I want you to pay attention, right? Then how to make smooth surface? Compared to making pet bottle like this, the die is very difficult to make. These are much easier material because polymer melting temperature is much, much lower, right? Right? This is probably blow molding, different process. But anyway, so this is, permanent mold casting. So key is two kinds of casting processes, and then also they are differentiated, the usage wise, based on the principle and application. Any questions? I think that's kind of, end of chapter 3, and then, I can move on to chapter 4. And then, yes, I passed chapters, section 3.8 through 3.10. It's important. I want you to read, I want you to learn, but we cannot just cover everything. So, which means I am not going to include in the exam. But it doesn't mean you don't have to study. Make sense? There are two different things, because I have to select which one is more important, and probably you will use more. Okay, so let's move on to chapter 4. So chapter 4 is, oops, thank you. Good. So chapter 4 is more like a showcase, what process, how we can use. Because we studied rolling, right? We did some calculation. Chapter 5 is going to be like that. So what kind of process, what kind of force, power required, but to calculate, you have to understand how process works. So that's why chapter 4 is more like a showcase, how process each kind of, I would say like this is, metal forming technology. What kind of process we have and then how it works. That's this chapter 4. That's why it's kind of, quick, we can cover. So metal forming technology. So some of them are kind of, like duplication, but still we need to remember. So hot forming comes first. So hot forming, rolling, and forging, Right. So why we have to make material hot, right? Hot forming, right? Try to reduce, the yield strength. Right? Because you are deforming, Before was casting. Casting, you are melting. So now you are not going to melt. You are making the material a little bit softer. Softer means deformable. So like yield stress, strength, So if you can make it lower, it's easy to deform, right? So that's, hot. So that means lower or low, yield strength. Okay. So then how high you can bring? Of course, it depends on the workpiece, because below the melting point. But let's use some example. Like steel is always the good example. Steel. So it's going to be high temperature. But if it's very high, okay, it's not melting. Okay, like below. If you bring very high, then maybe you may overheat. No, because once you heat up, grain grow, right? And then going to be like recrystallization, and then you can have more kind of uniform like structures, and then you can deform. But it's very high, overheat, and then if you go exceeding, and then maybe grain boundary, they are going to have some sort of segregation, depends on the like composition, and then it's going to be granular, and then after that, what's happening? It's going to be burned. Basically, if you say burning, again, this is still not melting, but you cannot, you cannot fix, let's say repair. You cannot repair the mechanical property or even structure of the steel because you burned. So again, segregation happening and grain crumbling, and then it looks steel, but maybe not as strong as you want. So you have to prevent this burning. So you cannot repair if it's burned. So what you can do, you have to do, not throwing away, you have to just melt back to the original state, which is melting and then remake. That's going to be costly, right? And maybe you cannot make it in your shop floor. Then you have to send back for recycling company or maybe steel manufacturer. So anyways, hot forming, yes, we can lower the strength, but temperature control has to be very careful. Okay. And then once you burned, so then I said like a crumbles, right? Workpiece, and then this stage, let's see. So workpiece is going to be like maybe crumbles, So this, it's you see this stage, it's called it's a hot shortness. That's just kind of like steel burned and then crumbled. This kind of phenomena. It's called hot shortness. Okay. So another key maybe like really high temperature you have to care. Yes. So the grain boundary depends on the like your compositions. So all the first grain grower, right? And then going to the grain, still grain has it's not like one. And then all the some chemical composition going to grain, and then some sort of segregation show up. So it's going to be like a crumbling, eventually. Yeah. So then another thing. So for steel wise, you have to maybe pay attention. It's oxidation. For some reason. Now what? Okay. Okay, I'm just going to save. Okay, what I want to say is oxidation, because I don't want to waste time. And can I just now type? Oh, good. So we talk about Fe2O3, Fe3O4, FeO, right? So we call sometimes the scale, right? Kind of thick, kind of dark color, like a blackish color you saw before. So that's, you have to machine, right? To remove, because it's like really, oxidation is not like a flat layer. So maybe, you have to, do some secondary process, but you need to pay attention. So again, Fe2O3, reddish, 3O4, and FeO, it's like kind of color-wise, blackish, So that's maybe you can, separate. Okay, so anyway, back to this steel, So, key-wise, so then how we manage, So then first, not very that high temperature, and then grain size, right? Grain is going to recrystallize, and then going to control. If you control the grain size, which means you are controlling mechanical property, right? Then, depends on that, you have to do heat treatment, but you can maybe control. So if you control, then this, hot forming, no idea. What's I know you're frustrated. I'm so sorry. This is not my plan. My plan is like this. Okay, then, you can control, high yield strength, and then fracture toughness, toughness, and then lower, internal strain and stress. Okay, that's what you want to have, So fracture toughness also high side, fracture toughness, Okay. So anyway, that's we can see figure, figure wise, figure 4.1. Okay. So let's take a look at page 179. This is figure 4.1. So this is the hot forming temperatures. So this is range. So again, you cannot do hot, right? So upper limit, you can read this page, like 4.1.1. But this is an example of carbon content, and then like a steel case maybe, and then this is 723, right? Remember, this is a kind of eutectoid point, something like that. So, but anyway, upper limit, about 200 to 300 degrees Celsius below the solidus line. Okay, and then lower limit above, this is gamma to alpha transformation line. This is a steel case. So there is some range, recommended range. Again, upper, because lower, if you don't heat up enough, maybe you still have to put a lot of force to deform, right? Then maybe like non-uniformity may show up, stress, So that's probably, you want to avoid. Okay, and then, figure 4 point, maybe that's, because now we have already 139. So anyway, I think today I want to finish this. So Wednesday, I said course review, but I still want to cover certain material which I plan. So we will do, cold work, so section 4.1.2, and then some calculation exercise show up. Then after that, maybe we can switch to, exam information, and then also reviewing the material together, what's more important or less. Yeah, so two, but I still want to cover,
No, that's fine. I was trying to make sure Friday was still.
Ah, yes, 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 correct, yes. Yeah, yeah. Okay. Yeah, no, sorry about that. Yeah. Okay, thank you and see you on Wednesday.